Hello everyone and welcome to the third part of our high dimensional statistics series. We are still in the first part about the curse of dimensionality. We have seen how the increase of dimensionality distorts the notion of distance, and we have dismissed the trivial solution of adding more observations. That was due to lack of resources and feasibility. Right now, we will see the last two aspects of the curse: the cumulation of fluctuations, and the concentration of the mass in the tail, or the crust. Let's start with the fluctuations. Suppose we have a population of employees in a city, and we would like to estimate the expected value of the salaries of all employees. Since we usually don't have access to all the salaries, we use a small sample, and we calculate the mean. For instance, if we have a sample of 5 people, this is how we do it. Generally, the empirical mean is a great estimator for the expectation. It checks all the boxes. But what happens to the performance of this estimator if we increase the dimensionality of our data? Let's assume we have a bunch of data with dimensionality p, and with covariance matrix equal to some non-negative value sigma multiplied by the identity matrix. Let's evaluate the mean squared error of the mean estimator and see if we can find a link between it and the dimension p. Let's assume we have p variables containing n observations each. Don't let the notation fool you. This is pretty simple. The first column is the first variable, and the last one is the variable of index p. The mean of a variable g is equal to the sum of values divided by the number of values, which is n. Now, how does the dimensionality influence this mean squared error? So the mean is nothing but the estimation of the expected value. A straightforward calculation gives us this result. The mean squared error is equal to p multiplied by sigma squared. So the mean squared error does depend on the dimensionality. And when you are estimating something, you need this mean squared error to be as small as possible in order to have a close idea about the real value of the quantity we are estimating. And here, if p is big, then our mean squared error will also be big. Let's explore this by a simulation in R, in which we will simulate observations and we will observe how the mean squared error changes with the change of p. As usual, I will go through the code line by line before we run it in RStudio. We use the package mass. Particularly, we use its function mvrnorm, which stands for multivariate normal distribution, in order to generate data that is normally distributed. We chose the standard normal distribution by setting the mu vector to all ones and the sigma matrix to the identity matrix, as our variables are going to be independent. We calculate the mean by using call-means, and we calculate an approximation of the mean squared error, and we calculate the theoretical value that we obtained for this error. Let's start with just small variables. Okay, with small variables, the mean squared error is 0.2. Let's increase it to 200 variables. It becomes 2. Let's get a little crazy with the numbers and use 2000 variables. It's going to take a little bit of time to calculate it. So what this means is that the more dimensions we add, the more unreliable our estimation of the mean becomes. So we cannot count on the classic estimator of the mean to give us an idea about the expected value, because with the addition of new dimensions, this mean squared error increases and our estimation becomes really unreliable. Now it's time for the last curse, the mass concentration in the tail. Suppose we have a point in a two-dimensional space. This point is the center of a unit ball. We are interested in the surface of the highlighted zone of this ball, which is of width 0.01 centimeters, for instance. The rest of the unit ball is a unit ball with ray equal to 99% of the original one. We want to see how the ratio between the volume, the surface in our case because we are in a two-dimensional setting, the ratio between the surface of the highlighted zone and the surface of the ball, and see if it's going to change in function of the dimensionality. After a simple calculation, the ratio is equal to 1 minus 0.99 to the power of p. Yep, p interferes here too. Let's plug in different values of p and see how this ratio changes. For p equal to 2, it's roughly 2%, which makes sense as we can visualize. Now let's take p equal to 3. This value becomes 3%. And for p equal to 5, it's 5%. Now let's jump to 20. Man, that became 18%. Remember, the crust is only the length. Now let's jump to 20. Man, that became 18%. Remember, the crust is only of length 0.01, like we have previously explained, and despite that, we have an unreasonable inflation of the ratio of this crust to the volume of the ball. Do you guys think it will continue to increase? You guessed it right. For 100, it's 63%, and for 1000, it's 99.99%. The crust devours all of the mass in our unit ball, which is crazy to be honest. This has tremendous implications on probability distributions, as the tail of these distributions, used to model real-world problems, will concentrate all of the mass, which is a big problem in the math world. Here is a representation of the evolution of the ratio of the crust and the volume of the ball. It literally becomes 1 at a certain point. Thank you for your time and attention. Stay tuned for the next videos, which will be about how ordinary least squares regression falls apart in a high-dimensional setting.